Good morning. Today we're going to continue on in Chapter 5, talking about Section 5.3, Polynomials and Polynomial Functions. Alright, the first thing I want to do is define what a polynomial is. Before we do that, I want to define what a monomial is. A monomial is a product of powers, and there could be more than one, of variables, and we could have more than one, and coefficients or constants. Example: 3x squared is a monomial. It is a product of powers and of variables and constant. This monomial is of degree 2. And we often classify these monomials according to their degree. And of course, the degree of a monomial is the exponent you see on that variable if there's just one variable. All right, so I'll write down the degree of a monomial is the exponent on that variable if there is one variable. All right. I'll give you another example of a monomial. Minus 5 a squared b cubed. This is also a monomial. It has more than one variable, but it's still a monomial. All right, this monomial has degree 5. This is a monomial of degree 5. All right, now if a monomial has more than one variable, the degree, as you might expect from this example, is the sum of all the exponents. Okay? Let's do another example of a monomial, and let's classify it also. Minus 2/3 r squared s cubed times t. Alright, this again is a product of powers of variables and constants. So this is a monomial. And yes, monomials can have more than one variable. And if I ask what is the degree of this monomial, well, don't forget, if you've got a variable with no explicit exponent stated, there's an implied exponent of 1. So if I add up all these exponents, 3, 4, 5, 6, this is a degree 6 monomial. Another example. Let's say the constant 7. Well, I could consider this a product of powers of variables and constants if I rewrite it like this. 7, I could write it as 7 times x to the 0 power, and since anything to the 0 power is 1, these statements are equivalent. Alright, so this 7, just the constant 7, is a monomial of degree 0. We'll see that exponent is 0 there. So this is a monomial of degree equals 0. So any constant is a monomial of degree 0. Okay? Alright, so we've defined what monomials are, and we know how to classify them by degree. Let's talk about polynomials. Well, the Greek prefix poly means many, and once we've defined monomial, the definition of a polynomial is easy. A polynomial is nothing more than the sum or difference of monomials. Any number of monomials being added or subtracted together is a polynomial. Okay? For example, x squared plus 3x plus 1, I call that a trinomial because it is a sum of three monomials. Now, classifying trinomial or polynomial degrees is a little bit different. What degree is this polynomial? Well, the degree in general of a polynomial is the degree of the highest degree monomial it contains. So if I look at this term by term, where a term is a piece or element of a sum, this term, this monomial, is degree 0. This monomial is degree 1. Don't forget about that invisible exponent 1. And this monomial is degree 2. So I claim this is a trinomial of degree 2. Okay? Alright, so we've defined what polynomials are and how to classify them. Let's talk about some others. Let's say minus 3x squared y minus 2x. I claim this is a binomial. Bi for 2. And I ask, what's the degree? Well, it's a sum of two monomials, or a difference of two monomials. This monomial is degree 1. This monomial is degree 3. So when you're looking for the degree of a polynomial, it's the degree of the highest degree monomial it contains. So I claim this binomial is of degree 3. Again, don't forget about that invisible exponent 1, that implied exponent 1 on that variable y. Okay? Alright, this is a 4-term polynomial because it's a sum of 4 monomials. Okay. So I won't call it a quadomial, or when even more terms, quintomial or septomial. We'll just say if it's more than 3, we'll just cite the number of terms. I claim this is a 4-term polynomial, and the degree is what? Well, the constant is degree 0. This term is degree 1. This term is degree 2. And this is the highest degree term, that's degree 3. Right, so 4-term polynomial of degree 3. Let's do another example. Alright. Minus 4x squared y cubed minus 5xy cubed plus 2x squared y minus 2. Again, this is a sum or a difference of 4 monomials. So I'll call it again a 4-term polynomial. And what's the degree? Well, this monomial has degree 0. Any constant has a degree 0. This monomial has degree equal to 3, of course. Don't forget about that invisible or implied exponent. This monomial has degree 4. Oops, almost wrote 3. Don't forget about that exponent. And this term has degree 5. So we say it's a 4-term polynomial of degree equals 5. Remember, the degree of a polynomial is the highest degree monomial that it contains. Alright, so we've defined monomials, binomials, trinomials, and learned how to classify them. Alright, I want to talk about evaluating polynomial functions. Well, a polynomial function is simply something written out in function notation that is defined by a polynomial formula. For example, we read this as f of x. You may recall function notation from earlier math courses. F of x, it's not a product. In this notation, we read this as just like this, f of x. F of x equals 3x squared minus 1. All right, I claim this expression is a polynomial function because we define this polynomial in function notation. All right, as you probably know, the x inside the parentheses here is simply a placeholder for x in the formula that defines this function. For example, if I want to evaluate f of minus 2 for this above function, all I do is stick in a minus 2 or substitute a minus 2 for x and grind out a number according to my order of operations. All right? So minus 2 squared is 4. 4 times 3 is 12. And 12 minus 1 is, of course, 11. Alright, so evaluating polynomial functions is a fairly simple process. We usually reserve F, G, and H. Those letters are reserved for function notation. That's pretty much the syntax that's evolved over the years. Alright, so let me define another function. G of x equals minus x squared minus 2x plus 5. Alright, this is a polynomial function of degree 2, really a trinomial function of degree 2. And let's say I want to evaluate g of minus 1. Well, all I do is plug in a minus 1 for x, everywhere I see an x in that polynomial expression, and grind out an evaluation according to my order of operations. Now be careful about the negative signs here. Minus 1 squared is 1, and negative 1 is negative 1. Okay? Minus 2 times minus 1 is negative 2, and minus 2 is plus 2. And of course, add 5 as the last step. So minus 1 plus 2 plus 5 is, of course, 6. Okay? How about g of 3? Again, using the above noted g of x polynomial function. What's g of 3? Well, g of 3 is minus 3 squared minus 2 times 3 plus 5. Again, everywhere I see an x in my polynomial function, I now plug in that placeholder 3. Alright, 3 squared is 9, and negative 9 is negative 9. Minus 2 times 3 is negative 6. And plus 5 on the end. No x in that 5 term. So we'll get minus 15 plus 5, which of course is negative 10. Alright, let me squeeze, I want to keep this function here before I go to a new screen. So let me circle that in pink and grind out another simple evaluation. How about g of 0? Well, this we can pretty much do by inspection. I see if I plug in a 0, everywhere I see an x, I will get a resulting 0 evaluation at those first two terms. And 0 plus 5 is, of course, 5. So evaluating a function at 0 is sometimes an easy proposition. So there we have evaluating polynomial functions. Fresh screen. Adding polynomials. For example, I've got 3x squared minus 2x plus 4. That is a trinomial of degree 2. And to that I want to add 2x squared plus 4x minus 3. And I'm betting you've done stuff like this before. If we add polynomials, basically we'll just combine like terms. Combine like terms and simplify. Alright, I'm going to go term by term here. 3x squared plus 2x squared is 5x squared. Remember, when you combine like terms, you keep the variable portion and add or subtract the coefficients as indicated. Next, I'll combine the x terms. Minus 2x plus 4x is, of course, plus 2x. And 4 plus minus 3 is, of course, 1. Alright, so it's an easy proposition to add polynomials just by combining like terms. Of course, some of these polynomials get a little nasty. Let's look at an example here. Add minus 5x squared, let's see, x cubed y squared, minus 4x squared y cubed, plus 2x cubed y squared plus x cubed y plus 5x squared y cubed. So kind of nasty polynomial in two variables, x and y. This expression is a binomial because it's a sum of two monomials. This is a binomial of degree 5. Is it not? Reviewing our classification of polynomials. This polynomial, well, if you're adding 3 monomials, it's a trinomial. And let's see, this term is degree 5, this term is degree 4, this term is degree 5. This is also a degree 5 polynomial. Remember, the degree of a polynomial is the degree of the highest degree monomial it contains. Alright, let me erase the classifications because I want to be concerned with adding these polynomials. And again, to add polynomials, you just add the like terms together. Let's see, let me go to this and this. I see these are like terms. The variables and the exponents are the same in those terms. The only thing different is the coefficients. And of course, we'll just add or subtract the coefficients as indicated. So minus 5x cubed y plus 2x cubed y is, of course, a minus 3x cubed y squared. Did I say x cubed y? I meant x cubed y squared. How about this term here, highlighted in green? Minus 4x squared y cubed. Well, here's a like term with same variables and same powers, so I can just add those coefficients as indicated and keep the variable portion. So I'll say plus 1, do it yellow here, plus 1x squared y cubed, or I'll just write x squared y cubed, just redundant to write a coefficient of 1. And I'll notice there's a lonely little x cubed y here that doesn't combine with anything. It's an unlike term to any other term. So I'll just add it on to my final expression, carry it into my final answer. That term doesn't combine with any other term. So final answer, minus 3x cubed y squared plus 2x squared y cubed plus x cubed y. Add polynomials, combine like terms. Let's try another one. 1/4 m to the fourth plus 1/2 m cubed plus 3/4 m to the fourth minus 7/3 m cubed. Alright. Well, again, reviewing our classification here. This is a binomial because it's a sum of two monomials. Yes, monomials can have fractions in them. It's a monomial of degree equal to 4. Right? This monomial is degree 3. This monomial has degree 4. So I call this a binomial of degree 4. How about this one here? This is also a binomial. It is a sum of two monomials, and this is also degree 4 for similar reasons. Right? Alright. Let's go to adding these polynomials, these two binomials. Alright. Well, I see there's two degree 4 terms that are like terms that I can combine. So 1/4 m to the fourth plus 3/4 m to the fourth. Well, again, I'll keep my variable portion the same and add those coefficients in it as indicated. 1/4 plus 3/4 is, of course, 4/4. And I'll simplify that in a minute. And now I'll combine these degree 3 like terms. 1/2 m cubed minus 7/3 m cubed. Yes, you're going to have to subtract some fractions here. Well, it's going to be a multiple of m cubed. When I'll need to take 1/2 and subtract 7/3. Of course, I'll need a common denominator. Multiply top and bottom here by 3. I'll get 3/6 minus multiplying top and bottom here by 2. I'll get 14/6, and 3/6 minus 14/6 is, of course, negative 11/6, adding or subtracting these coefficients as indicated. So minus 11/6 times m cubed. Let me simplify this totally. Redundant to leave a 4 over 4. 4 over 4 is 1. 1 times m to the fourth is m to the fourth minus 11/6 m cubed. So that would be my final return for that problem. Alright, on we go. So we're now expert in adding polynomials. How about subtracting polynomials? Alright, polys is my abbreviation for polynomials. Let's say I've got something looks like this. I've got 9m to the fourth plus 16m squared. And from that polynomial, I want to subtract 12m to the fourth minus 18m squared. Alright, so this is a binomial of degree 4. This is also a binomial of degree 4. And I see I've got some like terms to crunch together here. Here I've got multiples here of m to the fourth power, but before I do that I have to deal with this negative sign here. What I'm going to do, and this step we can often do in our heads, I'll go ahead and write it out here the first time. When you subtract a polynomial, as you probably know, you can distribute that negative sign through that polynomial expression and change the sign as indicated. Essentially negate or opposite all those terms in that subtrahend. Alright, so negative 12m cubed is negative 12m to the fourth power is negative 12m to the fourth power, and minus 18m squared is plus 18m squared. Okay? So that's usually a first step, and we often do that step in our heads. Right? Once I carry through that negative sign, through that second polynomial, I can then combine the like terms. 9m to the fourth minus 12m to the fourth is, of course, minus 3m to the fourth. And then 16m squared plus 18m squared is 34m squared. Again, combining all the like terms. All right. So this is my final return for this polynomial subtraction. Minus 3m to the fourth plus 34m squared. Let's try one a little more difficult. Subtract the following polynomial expressions. Now we're going to have a lot of fractions here, so hang on. 5/2 w cubed plus 1/4 w squared plus 3/5. That is a trinomial of degree 3. And from that trinomial, I'm going to want to subtract 1/3 w cubed plus 1/2 w squared minus 1/5. Alright, so I've got a polynomial of degree 3, a trinomial of degree 3, minus another trinomial of degree 3 in one variable here. Well, as a first step, I'll simply rewrite the first trinomial and drop the parentheses, but again I've got to carry this negative sign through all three terms of the polynomial I'm subtracting. So I get minus 1/3 w cubed, minus a plus is negative 1/2 w squared, and minus 1/5 is plus 1/5. Okay? So now I see some like terms. I see a w cubed term pair, a w squared term pair, and a constant pair, which I should be able to combine. Let's take care of the w cubes first. 5/2 w cubed minus 1/3 w cubed. Well, I'm going to have to take 5/2, going to have to add or subtract those coefficients as indicated. 5/2 minus 1/3. Well, if I get a common denominator, multiplying top and bottom here by 3, I get 15/6 minus, of course I'll multiply top and bottom here by 2, minus 2/6, and I get 13/6 times w cubed. And that takes care of those w cubed terms. 13/6 w cubed. Now I'll see I can combine these w squared terms. Let me take off the scratch work here. I'm going to add or subtract two more fractions. I'll have to take 1/4 minus 1/2 and multiply that result by w squared. 1/4 minus 1/2. Well, of course, I'll need a common denominator, and that's 4. 1/4 minus 2/4, of course, is negative 1/4 times w squared. That's a 4 down there. Let me erase that. So that takes care of the w squared terms. And then 3/5 plus 1/5. 1/5 is, of course, 4/5. Alright, so don't panic when you see all these fractions. It's really not that bad, as long as you show your work clearly and go step to step. So final answer, 13/6 w cubed minus 1/4 w squared plus 4/5. And one more and we'll call it a day for this section. Another polynomial subtraction. Minus m to the fourth plus 9m squared. Minus m cubed plus 2m minus 4. Alright, again as a first step, I'll rewrite the first polynomial without parentheses, nothing really going on outside of those parentheses, so they're somewhat redundant. Remember, when you're subtracting a polynomial, to drop the parentheses, to free up those variables to combine, you've got to carry that negative sign through. So get negative m cubed minus 2m, and minus a minus is plus 4. Okay? Now I look to combine like terms, and there are none. Remember, like terms are terms where the variable parts and the exponents are the same and the coefficients are perhaps different. Well, there's only one m to the fourth term, there's only one degree 4 term, there's only one m cubed term, only one m squared term, only one m term, and only one constant, so nothing combines here. Alright, so the best I can do is rewrite this polynomial in standard form. Of course, addition is commutative and associative, so I can rearrange these terms in any order I like. Standard form means arrange the terms, or the monomials, in decreasing degree, and of course implies left to right. Alright, so if I take those terms and arrange them in decreasing degree, as long as I tag along that negative sign, I can rearrange these terms in any order I like. So I'll take the degree 4 term, and then the degree 3 term, then the degree 2 term, then the degree 1 term, and then the degree 0, or the constant term. Alright, so there's my final return. That's the best I can do for this problem. This is the simplest answer in standard form. It is a 5-term polynomial of degree equals 4. The highest degree monomial this polynomial contains is of degree 4. Alright, that brings us to the end of section 5.3, polynomials and polynomial functions.